All right, so jumping right into trusses, right? So trusses are going to be the ones where you, yes, everyone who's here at all counts, Carson. Trusses are going to be the ones that look like bridges. So you're going to end up having two structure problems. One is going to end up having a like bridge looking structure, and one's going to have some weird structure. The one that looks like a bridge is going to be the trusses problem. The reason I say that is because the questions are kind of similar, because you're going to end up asking, or you're going to end up being asked for the forces inside of, these members. And sometimes that can look very similar for trusses and internal forces. So identify which one's a truss by looking at it like a bridge. Now, historically, there's been problems where it'll look like a normal bridge, but it's got some weird little thing on the side of it that would make it look like no bridge would look like that. You know what I'm saying? So the thing is, if you see something like that, if you see something weird like this, know right off the bat that you can check to see if those are zero force members, because if you isolate this joint, there's two forces or two members at one joint where there's no loads, so those can go away. So it's essentially like those aren't there. So that's the trick that they threw at people last semester. So I just want to run through the steps really quick. They're already done out because this is the same notes that I used for the review videos. But step one is to draw a free body diagram, right? Which means I have to consider all the forces at my reaction. So in this problem, there was a force at B, a force at AY, and a force at AX. So all of that had to be translated down to my free body diagram. Remember, these are 3 points on your free body diagram. So please, dear God, do not forget those, because that was frustrating last time to see how many people forgot those. Yeah, so as long as you include the forces where the supports used to be, the forces that are loading the bridge itself, like all of those, if you include those, all your dimensions have to be labeled, which is kind of annoying, but they have to be there. And then your coordinate axis, that's all you really need for your free body diagram. So how many unknowns do I have on this free body diagram right now? Well, I have 3, which means if I expose any more unknowns, I have to be able to identify what these are. So sometimes that means I have to solve them. Sometimes that means I have to solve them first. And ultimately, once I cut them, I don't expose 3 more. But it depends on the problem. So always kind of look at what the problem is asking you for in terms of what members you have to find, and then see what reactions you have to find. Worst case scenario, solve for all 3. It's not going to be that cumbersome. You have the equations already. So here you had 3 unknowns, you have 3 equations, go ahead and solve for those, right? So some of the moments about A will get you BY, and then you can do some of the forces in the Y direction to find AY, and then some of the forces in the X direction to find AX. And in this case, AX is going to be 0. And honestly, in most truss problems, AX will be 0, or whatever X direction will be 0, because you're considering like a loaded bridge, not something that's like you're not considering normally a situation where a car is like braking on the bridge and that's applying a sideways force. So, I mean, they could technically do that, but I don't think they will. So usually AX is 0 because there's no other forces going in the X direction. So at this point now I have all of my unknowns externally. So step 3 is to decide what method you're looking at. So I'm going to first go through method of joints, right? Because that was probably the first one you ended up learning. So let me actually go to here because I like this one better. So if you're looking at method of joints, okay, this is a mess. So if you're looking at method of joints, basically the idea is you're isolating joints like one at a time and seeing what you can do in terms of finding unknowns. So if I'm looking at this joint, I have two unknowns, as in I have this force here and this force here. And because I'm looking at a joint itself, it has to be that I only use two equations, because the moment equation here is useless because all my forces go through that point. So moment equations in a concurrent system are useless. So because of that, I can only use some of the forces in the y direction and x direction to solve that. Does that like kind of make sense? So the benefit to method of joints is that technically it's like simpler calculations, but in theory, you would have to do it a lot more times to get all of the joints in the bridge. So if you're looking at steps for method of joints, you draw the free body diagram of the whole thing, you solve for all the external forces, and then you isolate one joint on the truss, right? So that's what I've done up here. I've isolated one joint and I now have to draw that free body diagram. So there has to be one free body diagram for every system I'm solving. So here, now I'm solving this up here, where I have all my dimensions labeled, I have all my forces labeled, I have my little coordinate axis thing. Yeah, so that's everything I need. Then I acknowledge that at this joint, there's less than 3 members that I have to expose, right? Because there's 1 and 2. Because if I only have 2 equations, I can't have 3 or more unknowns. So the question then becomes, how do I solve for these, right? So you have 2 options. You can either start with some of the forces in the x direction or some of the forces in the y direction. I personally would start for the sum of the forces in the y direction because both of these unknowns have a component in the x direction. So because since AC doesn't have a y component, your y equation is only going to have AB in it, if that makes sense. So by solving for your forces in the y direction, you can find AB and then plug that into your forces in the x direction equation to find AC. And then once you're done, you move to the next joint. So the question becomes how do I know what the next joint should be? So if I have one here where it's like this, and one here where it's like this, and we're gonna let's call this B and this C. Which one should I solve for? Which one should be my next one? Exactly, C. Why, Carson? My guy, unmute yourself. But yes, there's less members. So because it's not necessarily just that there's less members, but here there's 2 members. And like I said, I only have 2 equations, which means I have the only option to solve this one. But by solving this one, I'll also find this member because these members are the same. So once I find C, or once I solve C, I can move on to B because now I only have 2 unknowns. So that's kind of the thought process surrounding the method of joints, right? So the idea is you're going to hop from one to the other all the way through and solve for them one at a time, right? Which is great if the question is asking me for these, let's see, 1, 2, 3, 4, 5, 6 members, right? So that's perfect because I don't want to have to make 4 cuts here and solve those. But if it's asking me for, say, like these members here, that's a huge pain in the butt because I have to start, oh my gosh, I have to start at one of the corners and then go from here to then somewhere probably here and here. Like I have to hop from joint to joint to joint to joint just to find the ones that are over here. So that's how you decide whether or not to use one method or the other. Look at which one is probably going to end up being less work. Now, real quick, let's go through method of sections. Again, this is a mess for some reason. So I'm just going to go through the steps real quick. So first, again, you draw a free body diagram of the system you're looking at. So here, I'm pretty sure I actually just drew those members on this bridge. Yeah, so these are the members I'm looking at, I think, on this problem. Maybe not. But yeah, so these are the members I'm looking at. And basically all I have to do is isolate them, right? So once I do that, none of these forces actually matter, right? So the alternative was I could hop from joint to joint to joint and solve them that way. But because I'm solving them with method of sections, I don't have to do that. So I can just straight go from one to the other. So none of the internal forces in those members matter. The only ones that matter are JK, JM, and LM, right? Because those are the ones we're assuming the ones that the problem asked for. So once I find all my external forces, so like I said, when you're looking at the initial problem, figure out what external forces you have and which ones you're going to have to consider, right? Because in this case, I didn't care what AY and AX were because I'm only looking at the side where B is, right? So if I took the moment about A and found BY, I'm done because I just needed BY for this system. So kind of like think about those steps at the same time. Don't actually cut it yet, but identify which ones you're going to have to cut and then move forward from there. So basically moving on to the steps. So I've drawn my free body diagram. I've made my cut. I've redrawn the free body diagram for that. So I have all my components. I have my forces, my loads, my direction, my dimensions, and whatever this little thing is called, my coordinates. And then I have to evaluate the truss structure. So are there any zero force members I can get rid of? Because that's going to be something that, honestly, I would do that before you cut it because it would help identify where the easiest cut would be. So I would look at finding zero force members before you cut it, but then look again after if you really want to. So basically, once you find the zero force members, you look at the problem and verify which members you need to find the forces in. And usually they're going to be next to each other. Like, see how these I could cut straight through. Okay, so on the exam, what you're probably going to end up with is something like a question like this, but also they want this one, right? So what you're going to end up doing is you're going to end up solving with both methods. So you're going to cut here, right? Expose these forces, JK, JM, LM, solve for those, and then separately do method of joints here, which is totally valid because you're not using those internal forces in coordination with each other, right? So yeah, so basically the project. Exactly. So basically once you get to this phase, just going back into the method of section specifically, once you get to the point where you've drawn your free body diagram, you cut it, you have the right number of unknowns, you're ready to solve it, you take the moment. Remember, the moment, the whole point of using the moment equation is to cancel out two forces that have a common point so that you can isolate and solve for one specifically. So I have two options here. I can take the moment about like this point and solve for LM, right? Because JK and JM all go through J. Or what I can do is I can take the moment about M and solve for JK. So I have two options. So you're going to end up getting to a point where you're like, wow, I have like, there's two places I can take the moment about. It doesn't matter which one you choose. And honestly, you can take the moment about both of them. If you really wanted to, you could say, take the moment about J to find LM, take the moment about M to find JK, and then just do some of the forces in the X direction to find JM. So it doesn't necessarily matter how you solve for them. You just have to solve for them in the way that makes the most sense for you. And usually that, I mean, for me at least, that means one moment, one force is in the Y, one force is in the X. So that's what I did here. So I took the moment about J. So I took the moment about this point here. Oh my gosh. I took the moment about this point here and I solved for LM. And then once I do that, I can say, all right, well, I have this one. Some of the forces in the Y direction, there's only one force that has a Y direction, right? Because JK and JM are all horizontal. So JM is going to be easy to solve for. And then once I get to the sum of the forces in the X direction, I've already found LM. I've found JM. So now I just have to find JK, which is now the only one with something in the X direction that I don't know, because I've solved for LM in step 1 and I solved for JM in step 2. So that's kind of the process you go through for finding that. And then if the problem asks you for something else, you can either make another cut exposing those, or you can say, all right, I'm going to look at that joint or something like that. Does that kind of make sense so far for method of joints and method of sections? Does anyone have any questions about it? Do you think we'll have to label zero force members as a part of the question like the quiz? Probably. Another thing I think they might have you do is something like I said, where you have like the normal looking bridge and then you have this weird like thing coming off of it, and then it's asking you for the forces in, oh well, that's awkward. Pretend that looks symmetrical. They'll ask you for the forces in like this, and maybe even that. And you just have to identify that, because even if there's a support here and here, even if that's the case, there's nothing loading this joint or this joint. So these two forces are zero force members. So right off the bat, you should say that. Honestly, what I would do is I would draw like a little thing through it, like you've always had to, if it's a zero force member, and then redraw it without them. So the next step would be like, okay, so here's this. And now I have, oh my gosh, I'm struggling. But so now I have this bridge without it. And then from there, like my diagonals are still there. But from there, solve for the members they've asked you to solve for. So I would make it a step even if they don't ask you to, because that could be partial credit. You're welcome. Okay, so going through
on one of the review problems.
Yeah, what's up?
Well, it's hard to explain without showing you. But
okay, do you know which review problem it is?
Yes.
What is it?
Is
it in like the review module?
Yes, and it's the first truss problem.
This one?
Yeah. So finding the zero force members here, I thought it says that HB is a zero force member, but if that's the case, why isn't JD a zero force member?
Okay, so HB is a zero force member because if I'm looking at, for example, if I'm looking at the rule where if I have three members that meet at one joint and two are collinear, that's the situation I have. So here's my joint. Those two are collinear. The third one is going to be a zero force member. Does that make sense?
Yes.
So same logic could apply to here, right? Which is what I think you're seeing, except this joint is loaded, so we can't even consider that. So there's a force here, and there's not one here. That's the difference. So you can't
so it
even
doesn't matter if the force is coming from the top or the bottom of the truss.
No, so I'm isolating joint B and joint D. So those are the two that I'm loading. So joint H doesn't even matter in this situation because I'm cutting it basically the equivalent of right here.
I see.
So same thing with here.
Right.
So by that logic, what I could try to do is I could see like, well, is there a way for me to see if I would cut it here, if that would work? But I have 4 joints here.
Right. So the 1,000-pound force doesn't even touch joint B. Is what you're
this
saying.
One?
Yeah.
Yeah, that one. Yeah, because this is a zero force member. What you can assume is that that entire 1,000 pounds goes through AHG or HC as it's loaded right now. GC would be a zero force member. No. Because if I'm looking at G, I have 3 joints, but none of them are collinear, so I can't use that. And if I'm looking at C, I have 5 joints, and none of those are zero force members. So I can't make any conclusions about GC. So don't just assume that because there's a giant vertical one right in the middle, that that's a zero force member. Because here it's not. So follow the 2 specific rules.
And it must be 3 members coming together. Otherwise, you can't decide whether it's a zero force member. Is that correct?
So that's one of the rules. The second one, which is one that they're probably going to throw at you on the exam, you throw, like, if they threw something like that just to throw you off, what they could do is put that there. But if you isolate this joint, because there's 2 members meeting at one unloaded joint, that would be a zero force member. Like both of these would be zero force members.
Okay.
Does that make sense? So there's 2 rules, and I'll go through those in a second. But to answer Lauren's question, is HC1. So good question. So after I've decided that this one's gone, right? Now I can look at joint H, because that's what you should do. You should do both rules and then go through and then look at both of them again. Because here, technically, if this 1,000 pounds wasn't here, I would have 2 collinear members and a non-collinear member. So if that 1,000 pounds wasn't there, HC would be zero force member. But because that 1,000 pounds is now loading joint H, which I am now isolating, that would be the joint I have to consider. So before, I didn't have to consider that 1,000 pounds because I was isolating B, and that 1,000 pounds wasn't at B. But to determine HC, I would have to isolate H or C. So I can't use H because it's loaded, and I can't use C because there's 5 joints there. So I can't conclude that HC is a zero force member. But JC would be. Not necessarily, because the only reason I was allowed to even look at HC was because we already got rid of HB. Because if I try to get rid of JC, I can't, because this is still there because this is loaded. Does that make sense? Cool. So if this bridge wasn't loaded at all, if this was the only load, so if we were going to pretend that this 1,000 pounds wasn't here and this 1,000 pounds wasn't here, you guys are right that this would be a zero force member, this would be a zero force member, and then these would also be zero force members. But because those loads are there, we can't conclude that. Oh, also because now that I've eliminated these 2, this would also be a zero force member because now I only have those 3 at this joint. So those loads being gone simplifies it a lot. Does that make sense? Anyone have any other questions? Cool. So my recommendation would be to pop through these questions, or pop through that process a few times, just so you can make sure that you're not unleashing another situation where you could simplify it more, you know what I'm saying, by eliminating one. So let me just real quick summarize those 2 processes, right? So a zero force member, remember that those are only there to help with variable loads. And when you're looking at a free body diagram, that is not a variable load. That's like a screenshot of something happening, like a screenshot of a loading condition. So that's why we're allowed to get rid of them, is because if there's no variable load, there's no use for them being there. You know what I'm saying? So the first like process that you can use is like the two members meeting at one joint. And all of those, like three examples of that situation are happening here, right? So first one is we're looking at A, and this one we're looking at, I guess, also A. So that's two cases, right? So automatically, if there are no loads at those two joints A, then we don't care about either of these. They're automatically zero force members. So AB and AC would be zero force members. The third case I'm going to get to in a second, like this case here, I'll get to in a second. But the general process is isolate a joint that there's only two members at that joint, right? And then you have to verify that it's not loaded. So if it's loaded, you can't make a conclusion. There's no zero force members. But if it's not loaded, draw your free body diagram like normal, but then the members that meet there are zero force members. So if you're looking at a larger structure, like the whole bridge itself, you don't have to draw a free body diagram. You can just draw like this thing through that joint. But if you've already drawn a free body diagram, make sure you include all the components and then decide that they're zero force members. I'll come back to that purple. The 3-member rule is similar, right? So I have 2 collinear and 1 not. The one that's not collinear is automatically 0. So this one here would be 0 because it's the one that's not collinear. The thing that I want you guys to remember is that it doesn't always have to be perpendicular. It could be something that looks like that even. And if you're looking at this joint, these two are collinear. This one's not. So it doesn't always have to be pretty and like perpendicular and stuff. That's just usually the way bridges work. So yeah, don't freak out if you see something like that where it's like not perfectly like, what am I trying to say? Like laid out exactly like this one is. So again, the general process is you pick one joint where 3 members meet, and then you identify, is it loaded? If it's loaded, there's no zero force members because you can't decide that. If it's not loaded, ask yourself, are 2 of the 3 joints collinear? Because that's inherent to the rule. So just like in the problem before, we had something like this, we can't decide that because none of those members are collinear. So just because there's 3 members meeting at an unloaded joint doesn't mean you can use this rule. 2 of them have to be collinear. Cool. So once I go through both of these steps, what I want to do is I want to come back up to this one and say, all right, is this case something that I've now exposed, where I had a joint with 3 members, but I decided that this one was a zero force member, because now I have 2 members meeting at an unloaded joint. So I have this one and this one meeting at an unloaded joint. So now both of those are zero force members. So that's something you want to remember, is that you want to keep coming back to these rules and see, like, even come back to this one again, do it a couple times, because my issue on my exams when I took it was that I didn't come back to it enough to get all of them, right? I just went through one the first time, one the second time, and didn't consider what I might have freed up in terms of opportunities to cancel stuff out. So again, why do they matter? Because basically you can pretend they're not there, and that really helps you with the cutting process. So that's pretty much it for joints. Does anyone have any questions before I move into frames? No, doesn't look like it. Okay. So moving into frames, the process, I don't want to say is like simple, but it's like pretty similar every time. So that's a nice benefit. Keep in mind that on the exam, you're not going to have enough time for them to ask you for both a frames question and an internal forces question. So what that means is they're going to probably give you a more simple structure and say, okay, find, say, the reactions at pin B, right? So one part of the problem is going to say, find the reactions at pin B, but another part of the problem might say, and also the, let's see, the internal forces at this point F, right? So they're going to end up asking you for both. And what that means is you're going to have to end up solving for B first, right? Because when I take this apart, I need to be able to have my only unknowns at the cut itself. So that's generally what you want to do. I'm going to go through the general steps. So you always want to draw your free body diagram with all the forces taken off and look at it holistically, right? Because if there's only one unknown externally, what I can, or if there's less than 3 unknowns externally, I can solve for those right away. In this case, there's 1, 2, 3, 4 externally, so I can't do that. So I know I have to cut it first. So moving on, I pull the pins and I disconnect all the members. But what that means is now I've exposed the unknowns that are holding that pin together and in one spot, right? Which is why I have to put my X and Y unknowns in equal and opposite directions, right? So because when I put them together, I want them to cancel out completely. So they're going to be equal in magnitude and opposite in direction, kind of like I drew here. Does that make sense to everyone? That's going to be a common mistake. So just make sure you're checking yourself on that. So once I've drawn my free body diagrams, I now know that I can count my unknowns, right? So in this case, on this body, I have 1, 2, 3, 4, 5 unknowns, right? So I probably shouldn't start there. Here I have 1, 2, 3. So I would definitely start here, solve this one. And then I can move dx and dy over to this one because I know they're the same values. They're just in the opposite direction. And then after that, I have 1, 2, 3 unknowns on this one. So that's what I'm saying in terms of like it being a simpler example is that you can solve one entirely and then move on to the other one and solve that entirely. So we kind of already went through this process. So evaluate how many unknowns you have and where. You start with the one that's got 3 unknowns, which meant I had to look at this body. Because I have 2 unknowns meeting at this point, I'm probably going to take the moment about that, solve for CY, and then I can do the sum of the forces in the Y direction to find dy, sum of the forces in the X direction to find dx. And because this force here has an X component, you can't just say dx is 0. So then I'm going to move those over to here. So now I know these 2. And then what I'm going to do is I'm going to say, well, there's 2 options. I can take the moment about B to find AY, or I can take the moment about A to find BY. Doesn't matter. I think in this example, I took the moment about B to find AY. So I know that one now. Now I can do some of the forces in the Y direction to solve for BY, some of the forces in the X direction to solve for BX. And then that's solved. So then after that, my next process would be, all right, if I was told I'm going to cut it, or I have to cut it here, what I'm going to do is I'm going to find that on my free body diagram. So that's going to be on this free body diagram, which is probably somewhere around here, right? So looking at that, what I'm going to end up doing is I'm going to say, okay, I have this side of that force. This is point D. And I've made my cut through that. So I've exposed my 3 unknowns, my normal or my shear force, my normal force, and then my moment, right? But then I also have dy and dx. So then I can just solve those. What I could also do is I could also look at the other side. I don't know why you would want to, but what I can do is I can look at the other side and say, all right, well, I have my shear, my normal, and my moment, but then I also have 2 kilonewtons and By and Bx and 16 kilonewtons and Ay. So you could do either side. Just note that just like in the pin connections, these have to be equal and opposite from each other, because again, when I put them back together, I want them to cancel back out. Oh, Carson, I just saw your question. So if there's a pin on one side of cut, you can exclude all forces past that pin. You're talking about like in this situation? I don't really know what that question means.
Sorry, I realized my mic was on a different one. Yeah, that one. That's what I'm talking about. So like, you don't have to include any of the CY or anything else. You can just stop it at that pin because it's
exactly because you're looking at the forces inside of that member, and that member ends at joint D. So that member ends right here. Good question. So that's a simpler frames problem. That's probably what I think they're going to give you, because that's the only way they can reasonably incorporate the internal forces component. But in the off chance that they don't include that, I wanted to walk through a more complicated one, which is the one where we did this, like basically this laundry list of stuff to do. You know what I'm saying? So step one is to draw all of your individual free body diagrams, right? And you should have one for every single body on the structure, right? So that's this. So going through this, what I can do is I can say, all right, well, almost all of these have too many unknowns for me to solve. So if you're looking at BD, so this first one here, it's got 1, 2, 3, 4, 5, 6 unknowns for me to solve for. This one's got 1, 2, 3, 4, 5 unknowns for me to solve for. This one's got 6. This one's only got 2. So I'm going to figure out the one that's got 2 first, because that's easy breezy. So in this case, in the case of a pulley, you'll usually be able to solve those first. So I've solved for dx and dy, which means I've also solved for dx and dy here on BD. So now what can I do? Well, I can take, looking at BD, usually what you should do is assess the ones that you've just found unknowns on and do everything you can with that. So I just found unknowns on BD. So I'm going to keep looking at it and figure out what else I can do. So I can take the moment about B and find EY, because everything except EY will cancel or be known. And then I can take the moment about E to find BY. But that also means I know it here and here. What else can I do? So I've kind of done everything I can do with BD for now, because I basically have 2 unknowns in the same direction and I can't cancel them with a moment. So I can't really do anything else with BD. I found something on AC down here, but I only have that one value, and everything else, like this one's diagonal, and that makes it complicated. So moving on to CF, I can take the moment about C and find EX, right? Because everything will cancel in the vertical direction, and anything else, and CX will cancel. So EX I'll be able to identify. Similarly, I can take the moment about E to find CX. So now I know this one, but also this one. So then what I'm going to do is I'm going to go back to BD, right? And I'm going to solve for BX, because now I can just do the sum of the forces in the X direction and find this one. So the process is very it's kind of complicated unless you practice it, but the process is you just kind of figure out what you found and where else it is and what that will help you to do. So looking at ABC here, I now only have one unknown in the X direction, so I can do some of the forces in the X direction. And then I can take the moment about C on this one down here And then because everything else is known, I can get AY, and then I can take the moment about A and get CY. So now I have this one too. And the last step is just to do some of the forces in the Y direction on CF to find FY. So that's the more complicated problems. And I would absolutely, if you find yourself doing one of these problems, I would absolutely recommend writing out this list here, because if you end up running out of time, they'll at least know that you knew the mechanics part of it. You'll get points off for the math mistakes or like not having the math, but you'll know, or they will know that you knew how to do the math. I mean, the mechanics, which is what they're testing you on. Any questions about that? I kind of flew through frames. Questions, concerns? No? Cool.
Yeah, I have a question. So
oh, what's up?
We're automatically, the first thing we're going to do is pull the pins. We're not going to look for anything that we can solve like globally first.
Well, for this one, I wouldn't, because like in this case up here, that helped you a lot. Or well, in this case, you weren't able to. But if say B wasn't there, like ignore B for a second,
Right.
that would really help you a lot to have AY and AC.
Right. So if B wasn't there, we could take the moment at A to find CY.
Mm-hmm. And then at CY, or at C to find AY.
Okay.
But down here, it really wouldn't help you very much, if that makes sense, because yes, even if I found AY and AX, I'd still have 4 unknowns here. Mm-hmm. And even if I found FY, I'd still have 4 unknowns here. So it wouldn't really help me to find that, and I would still have to find for the forces in that pin anyway. Does that make sense?
Yes, thank you.
Cool. Anyone else? Good questions. Cool. Moving on to external forces. So, I mean, internal forces, yikes. So I kind of already showed you up here what I think they're going to do. And I think this is similar to what they did on the quiz, is they're going to give you some like fairly simple structure that looks something like this one. And they're going to ask you to solve for certain pins, but then also the internal forces at a given point. Like I said, you have to solve for the pins first and then solve for the internal forces at that point, because excuse me, when you cut it, you're exposing 3 unknowns. You're exposing the shear, the normal, and the moment, right? So with these being the forces you're exposing, you can't have any more unknowns. In terms of identifying which one's which, just remember that the shear is always across the cut, normal is always off the cut, and moment is always around the cut. And then it doesn't really matter which ones, like what direction in terms of like shear can be up or down. Normal can be off or like into it, and moment can be either way. You just have to know that if you're going to end up drawing the other side of that cut, they have to be opposite on either side of that cut, if that makes sense. So they have to be opposite each other if you're going to draw the other half of that cut that you just made. So any confusion in terms of actually identifying what the internal forces are? There's always going to be all 3 of these. Okay. All right, so looking at this, I've basically taken this example and I've cut it at E, which is what I was assuming, or what I'm assuming they wanted me to do in the problem. So I cut it at E, but note that I also cut through this distributed load, right? And because I cut through that distributed load, I have to consider what that means for the actual load itself. So if I'm finding my external forces up here, what I want to do before I even cut it is I want to look at this as a point load, right? So this is 2 kilonewtons per meter over a series of 5 meters, right? So it's going to be somewhere around here. And it's going to be 10 kilonewtons total, right? And then I can solve with my moment about A to find dy, some of the forces in the y direction to find ay, some of the forces in the x direction to find ax. So now I know all my external forces. But once I cut it, I can't just assume that 10 kilonewtons just because it's on that side of E. I can't just pretend that distributed load's not there, because I'm also I'm also cutting that distributed load, and part of it is on this side of the cut. So that means that not all 10 kilonewtons is over here once I cut it, and that means that there is some over here once I cut it. So that's something to consider. And that's probably where they're going to incorporate distributed loads, because that's something that is more conceptually something that you should understand. So by cutting your distributed loads, you end up having to reconsolidate them into a point load over which they're like distributed, right? So here I have 2 kilonewtons over 3 meters, which means at 1.5 meters, I'm going to have 6 kilonewtons. And here I have 2 kilonewtons over 2 meters. So at 1 meter, I'm going to have 4 kilonewtons. So they both add up to 10, but because I cut them, they're going to be different. And again, notice that my shear forces are opposite each other. My normal forces are opposite each other. And my moments are opposite each other. And that's again because we're in statics, right? So this wasn't moving to begin with. So when I put these back together and I basically uncut it, I want all those forces to cancel. So then it becomes a question of which one do I want to actually solve? And technically, it doesn't matter which one you choose, right? As long as you choose one. But I generally recommend, especially in the interest of time, I recommend solving for the one with fewer unknowns on it. So now, or fewer forces in general on it, because if I'm going to take a moment, I don't want to include 50 forces. So if I'm looking at this, luckily I have really 3 forces on this one and 2 forces on this one. So it's not that big a difference. But I have, like, I personally would choose this one because of the fact that it has fewer forces on it. So then once you do that, you just solve using basically your equilibrium equations. So some of the forces in the y direction to find the shear, some of the forces in the x direction to find the normal, some of the moments about d to find the moment. Questions about that? Any questions? So basically, even though I drew them out here, I drew both of them, I only care about one. So if you're looking at the structure and you're saying, all right, well, I know I'm cutting it at E. D is shorter, probably has fewer forces on it. I'm just going to do D. You don't have to draw this at all. Bless you. You don't have to draw this at all. Only draw the side you actually care about. But what that means is when I get to my answer, when I get my shear force is what we're going to call it 5 kilonewtons. I have to say 5 kilonewtons down on ED because I have 2 shear forces, technically. Questions on that before I move into cables? Actually, I'm going to move into friction and then cables. Okay, cool. So moving into friction, this is probably one of the more difficult topics according to like the results of the last exam. But if you're looking at a friction problem, it's very similar to what you did in physics 1 with just an extra step involved, right? So you draw your free body diagram normally. there's a couple things that you have to remember is that weight always goes straight down. So it's always going to go, whether it's on a slope or not, it's always going to go straight down, like vertically. The normal force is always going to be perpendicular to a slope. So those two are two that get confused a lot. And what I would recommend is, I know some people were drawing it like, if this was my surface, people were drawing the weight like this and the normal force like that. I would always recommend drawing them in tension. So like basically like I have it here where they're pulling on the center, not pushing on it, just because the center can get really crowded with a bunch of arrowheads in it. So that's that. And then the friction is always going to obviously be on the surface, like the interface between the surface and the box, and is always going to be trying to prevent you from moving it, right? So it's going to be opposite the direction of motion. You're not always going to know the direction of motion, so you might have to assume it. Doesn't matter. So, and then any other applied forces you have will also have to go on that free body diagram. Let's see. Any other recommendations? Okay. So one big thing that you're going to have to consider here is resolving your stuff into components. And the benefit of, I would recommend using like this kind of structure for your like orientation, as opposed to like the normal X and Y, because really the only force that shouldn't be parallel or perpendicular will be weight, or sometimes your applied force. So I would always resolve it into, I would always resolve it into parallel and perpendicular instead of X and Y. That's pretty much what that was. The process is the same. And then I'm probably going to skip all this because that's not necessarily helpful, but what we're going to end up doing is we're going to think about what conceptually can happen. If I'm pushing on this top corner of this box, I can either slide, I can successfully push it across the ground, or what I can do is I can cause it to rotate about some point, right? So I have to consider both of those situations. So the first process I'm going to do is I'm going to assume that I'm successful in causing the box to slide, right? So I'm assuming that this applied force here is going to cause this box to slide. Well, technically, because of the direction I'm assuming friction is going, I'm assuming that even though I have that applied force, I'm going to end up with the box sliding down the slope because of the slope itself. So kind of a weird situation the way I drew it. But when you're assuming that it's sliding or tipping, you want to calculate F max, which is through this equation here. And you want to compare it to the actual friction force that you got in this situation, right? So if the maximum friction is greater than the friction you found, you've surpassed the point where, did I draw this backwards? Hold on. F max is greater than or equal to P. No, you're okay. So if the maximum friction is higher than the friction you haven't yet reached this point up here where friction is switching from static to kinetic. So it's not moving yet. If your maximum friction is less than the friction that is there, you're moving, essentially. So P is causing it to move, or the weight pulling it down the slope is causing it to move, doesn't matter. Second situation is you're going to assume that the box is tipping. So if the box is tipping, you want to find out where this D perpendicular is, right? So basically what I'm going to look at is a moment about whatever corner I'm assuming it's slipping, where my unknown is going to be this distance. And it's going to be the distance between the side of the box you're assuming it's tipping about and wherever your normal force is going to be. So again, the situation here is if that distance puts the normal force outside of the dimension of the box, it's going to tip, because the normal force is there to support you, or to support whatever is moving. And if whatever's moving is being supported not from under it, it doesn't mean anything, right? It's not supporting it really. So basically it's going to be useless having that support there. If the normal force is within the box, or like under the box, or within the dimensions, however you want to think about it, it's still supporting the box, so it's not going to rotate. So those are the conditions. Friction, probably I think it was 2 and 3, you got into 2 different topics, right? So you got into questions where it was like, find the minimum amount of force that will cause it to move, whether it's tipping or slipping, right? Which means I'm going to have to find a value of P to cause each of these conditions to happen. And then I'm going to have to find which one is smaller. And the smaller one is going to be the first one to happen. So that's going to be the smallest value of P that'll get it to move. And then what else? You also got into like belt friction, right? And belt friction is something that some people get really, really confused about, just because of like identifying what T1 and T2 are. But I hope to explain it in a way that's a little bit more digestible. So basically, this equation is always going to be true for belt friction. So break that out every time you see a belt friction problem. That mu is going to be mu sub s every time, because we're in statics. So mu sub s, don't use mu sub k, they'll give it to you, but don't use it. That beta is going to be the total angle that the belt is touching some surface, right? So you guys had a couple problems where it was like that, and this, and there was some belt that went like around these, basically. So that contact angle is going to consider the fact that that's here, that should be here, and that's here, right? So that's going to be the sum of the angles that it's touching the surface. That's probably the hardest part of this problem. The other thing you have to consider is it's usually these questions are asking you for some kind of range of values of your applied force to keep the object stationary, right? Which, kind of like in the other friction problem that we were doing, you have to kind of consider impending motion. So not that it's actually moving, but if it were to move, what would it be? So if I have a situation where I have pretty much what I just drew, I don't know why I erased it. So if I have this, and this, right? And I have my applied force at the end of this cable and a weight hanging down here, right? So if I have some P and I'm pulling on that to counteract the weight of some box hanging or whatever, and I want to find the range of values of P to keep it from moving, I have to think about it kind of conceptually in the sense of if I'm looking for the smallest value, right? So what happens if I pull less than the smallest value? Someone answer that. So if I'm pulling, but it's less than the smallest value to keep the box stationary, what happens? Right, so this box is going to move down, right? So whatever I'm looking at here is going to move down. So if this force is intended to support that box, not supporting it enough will cause it to move like this way, and ultimately down. So which force is in the direction of that motion? So if the box is moving down, which force is in the direction of that motion? Exactly. So the weight is going to be the force that's in the direction of motion in this case, which means that P is in the opposite direction of motion for my applied force, which makes sense because if I'm pulling on it, but it's moving that way, that makes sense. So the opposite condition is, all right, what happens if I'm pulling a little bit harder than I need to keep it in the same spot is I'm going to end up pulling it too hard and pulling it up a little bit. So this is now my motion, right? So my hand here that's pulling is going to start moving that way, and it's going to cause the box to ultimately move up. So because of that, my force that's in the direction of motion is going to be, did I goof? T1 opposes motion. Yes, I wrote these backwards. The logic was right, but I wrote it backwards. So the force that's in the direction of motion, or the T2, is going to be this P, and the force that's opposing motion in this case is going to be weight. Sorry, I confused myself writing it down, because usually what I do is I visualize what's happening and I find out what's in the opposite direction of that. So T1 is always in the opposite direction of however you're moving. Questions about that? Usually this is where people get stuff backwards. And quite frankly, it's not the end of the world if you get stuff backwards, because this number, in like this case, P will be some value, we'll call it like 5. And in this case, P could be like 3. And you know the largest value can't be lower than the smallest value. So you know that these are backwards. You just switched your T1 and T2. So it's not the end of the world, just like switch it on your paper so that they know you acknowledge that it's backwards. Questions about friction?
Of like the 3 types of problems, which one do you expect to like be on there?
Oh wait, what happened?
Like of like the 3 types of friction problems, which one do you think would be on there? It's like they had like the ones where you're given P, the one where you're not given P, and then like the belt one. Or would it be like a combination of them?
I don't think it can be a combination of them. What I think is going to happen is you're either going to be asked for P, so either that second case where you have to solve for P, like solve for like the smallest value of P that causes motion, or you're going to be asked for belt friction. I don't know between the two which one will probably happen, but I would bet that it's one of those two. Probably the one where you're asked to find P. Because if you're asked to find P, that kind of gets into the same logic as belt friction, but this entire process of not belt friction, if that makes sense. So they get a little bit of both.
And this formula is on the handout?
I believe so.
Okay.
Let's look. Reference code. Friction. Yeah, so it's right here. It's written a little bit differently. So basically all you have to do is multiply both sides by T1. So T2 equals T1 E mu B. But it's the same thing. It's on, I think, the second page. Yeah, second page. Good question. So I'm going to move into cables unless anyone else has questions. No? Cool. So looking at cables problems, a lot of it is going to end up being trig, which kind of sucks, but it's life. So there's a couple things that you should know immediately right off the bat. The maximum tension is always going to be one of the two end strings, right? So it's always either going to be, in this case, this one or this one. And it's going to be the one that has the highest slope. So in this problem, we don't know what this YC value is, but once we find it, to find the max tension, you find which one has the highest rise over run. So this one is a rise over run of 1/3. So this one, as long as YC is something that would get it greater than 1/3, you're good. So that's the highest slope, which correlates to the max tension. So that's one thing I wanted to define. This problem, I believe, was the one that used that tangent theta thing, where it was like, because we didn't know this angle, or I don't think this tension, so because we had both of these unknowns and they ended up being related to each other, we had one equation where it was sine, or like TCD sine theta equals blah, 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 and then TCD cosine theta equals blah, blah, blah. And then by dividing these, we were able to cancel the TCDs and just get it to tangent theta equals whatever, like the rest of the equations divided. So that's definitely something to keep in mind, but I don't think that's going to be a very common practice on this quiz or on the exam. I mean, it's definitely an option that they have, but you've already seen it. So that's something I wanted to do, or to explain. In terms of the problem that they will probably end up giving you, my bet is that it's going to be something where it's not at the same height, because you actually have to get into more of like the mechanics part of it. So I would prepare yourself for that, but also know that you might not need to do it, if that makes sense, which is a really crappy answer because now I'm asking you to study for more things. But like I said, I haven't seen the exam, so I don't exactly know. All of it's fair game. So in this kind of situation, you can't necessarily just use one moment equation to solve for another unknown, right? Because if these were at the same height, I could just solve or take the moment about A to solve for EY, take the moment about E to solve for AY, and then we're good. In a situation where they're not at the same height, what I have to do is I have to find two values or two equations that relate the same two unknowns. So here, I took the moment about E, or they took the moment about E, and that allowed them to find an equation that relates AX and AY, right? Because we weren't able to solve for both of them because they're at different heights, so nothing cancels, but we can find an equation that relates them. The second piece that they ended up doing is that they ended up cutting it basically, and they took the moment about C, because basically what happens is when you're getting to this kind of situation, you can kind of treat these as like, I don't want to say you can kind of almost treat it like a trusses thing where you like cut it and you either do like method of joints or method of sections. So here they cut it, which is equivalent to method of sections, I guess. And they took the moment about C and they ended up finding an equation that relates AX and AY to that, because TCD cancels because it goes through C. So they have now these two equations that relate AX and AY, so they can solve those. So now they know AX and AY. Questions so far? Okay. So let's see. Then what they did is they cut it again, because remember the question is asking for the tension, or like the cable supports. They want to know the sag at point B and D. So basically they want this value and this value. And then the maximum tension in the cable. So like I said, the point where the slope is the highest. So what I need to know is I need to know this dimension and this dimension. Cool. So basically what we're going to end up doing is now I need to find the tensions in A, B, and D, E. So moving forward, that's what they did. They cut it at B. They took the moment about B to find the tension in, or they found the sag, sorry, by taking the moment. And then they were able to find TAB by relating the dimensions they got, basically. So that's
how do they know where to cut it, and then taking a moment about something and just eliminating all the rest of the other forces? Like, how are you supposed to know where to do that at, and why does that work if you're
okay? So think about it like a truss, right? So if I'm looking at the internal forces in a member of a truss, I can cut it and look at only one half of it so that the math gets simpler. But it is an internal force, right? So I have to cut it. Tensions are internal forces, so I have to cut to to basically expose that internal force. So for here, what I ended up doing, or for what they ended up doing, I guess, they ended up cutting this at essentially point C, so that they could only look at the left side because they wanted to relate an equation with they wanted to relate AX and AY. So basically they had these unknowns, and their options were, okay, I could cut it at B, but the problem is if I cut it at B, I now have a force going through A. So that doesn't help me. I can cut it at C, and now I have a force going through C, which gets eliminated, but I have my unknowns at A still. Or I could cut it at D, and then I'll have this, or my force through D. I do that arrow backwards, sorry. I have my force through D, which is valid, but it's more work because now I have to do more forces in my moment equation. So technically you can cut it, here or here. I think they just chose to do it here because it's less terms in your moment. Does that make sense?
Yeah, kind of. Thank you.
Yeah. And then down here, they chose to cut it at B because they wanted to find the sag at B, which means they had to write an equation that relates that, right? So by taking the moment about B and setting it equal to 0, they had, they had this term, this 5 newtons times this 20 foot distance. But then they also had this AX times the distance that they wanted, which was this sag. So it was a way for them to solve using one equation for the unknown that they wanted. Does that make sense? So you kind of just have to look at the system and identify what equation will get you to where you can solve for the one variable you want if it's possible.
Right, that makes sense. Actually identifying the variable, what you need.
Yeah.
In the equations.
Mm-hmm.
Okay, thanks.
So when you cut, you're cutting one point away from the opposite you're trying to solve and get away. Not necessarily. Carson, in this case, that statement's true, but don't use that as a general rule of thumb. Because if this had one more point, I could still cut. If this had if this went C, D, E, or something like that, it wouldn't do that. But if it did do that, I could still cut it at C and get the same thing. Does that make sense? So it's kind of like you want to find the closest one to the point you're looking at without going to the neighboring one, because then you'll have a force going through A. I don't know if that really helped your explanation or not. But does that kind of make sense? So this is the kind of problem that I would assume you're going to get on the exam for cables, is something with different heights. Any more questions on pretty much anything? Does anyone happen to know off the top of their head if I've uploaded here? Actually, I can just look. I just want to make sure I've uploaded the video for pulleys. I have not. So I will by the end of the weekend. So you guys have that explanation, but I have the notes. I just haven't recorded, I guess, or uploaded the video. So I will upload pulleys. I will try to upload cables by the end of the weekend, but everything else you should pretty much have. Any questions? On anything? So I know it's a lot of content, and there's been a lot of you who've reached out to me and said, like, what questions will they ask? There's a lot. It's all fair game. They could reasonably ask for one of every type of problem. So prepare for that. My recommendation for studying would be to try to put together, like, if you saw on here, every single like process that I explained, I put a set of steps together, like every single one, like drawing the free body diagram, like every process has a set of steps. Try to like put together a study guide basically of these steps, right? And once you get those, try to, I don't want to say memorize the steps because that's kind of not the move, but try to understand exactly where those steps come from and why those make sense. And by understanding inherently what the steps should be going into it, you can then focus your attention on the exam to like the little nuancey things that go into each problem. Does that make sense? So like, try to understand the general broad strokes of each process before the exam, but know that like, if the first exam showed you guys anything, it isn't necessarily going to be a straightforward problem in terms of like, yeah, like here's everything you might need to solve it, go solve it. Like there's little nuancey things, like you're probably going to get a weird angle or a slope triangle that you haven't seen before, stuff like that. It'll be something that you've seen something similar to, but it won't be identical. So get used to being not totally comfortable the minute you read the problem, but know that if you memorize like the general steps like this, you can always start and see what to do. Questions? Comments? No? You're welcome, Scott. No one's got questions? It's all Gucci. Love that. You guys are welcome. You guys have a great rest of your weekend. That's really all I had. I have office hours next week on Monday and Tuesday, or I guess this week, I don't know, on Monday and Tuesday. Feel free to come to those with any questions. And happy studying, I guess. You guys are all welcome.